Hello everyone, and welcome to the Post Lab. So this was the lab we just completed using a pivot to determine the relationships between the momenta of the two gliders after the explosion. And we were looking to see if there was a relationship there. And there definitely was a relationship. Now, I would have liked to have been able to do maybe 2 or 3 times as many explosions, but we did what we could with the pivot. Right? And we saw that regardless of the masses of those carts, regardless of what type of explosion it was, how strong the spring was, because we really don't know, right, in there, it seemed that always the momenta of the two gliders after the explosions were equal in size, but opposite in direction. This is the momentum of the left cart, final. Final just means after the explosion, right? And this is the opposite of the momentum of the right cart, final, after the explosion. Is that what you found? I hope so, right? That's kind of interesting, right? And it's only true of explosions. Now, things get a little complex, remember, because momentum is mass times velocity. So those momenta that are equal and opposite could be due to big masses or big velocities, or, there is some proportional thinking that can go on in there, right, that you're going to see when it comes time to do a concept builder in a little bit here. But I want to turn this on its head a bit and look at this in a little different way. Okay, rather than doing what we did in the lab, which is let's compare the momenta of the gliders, after the explosion. What if we called those two gliders a system, and we then compared the momentum of the system before the explosion, which I'm going to call P sub I for initial, to the momentum of the system after the explosion, which I'm going to call P sub F, final momentum. Now, a couple of things about my notation here. First off, we're going after or before the explosion happened and just after the explosion happens. Right? So we're not analyzing during the explosion. That's the what we found in the beginning of the unit, which is the impulse change in momentum theorem, right? That we can use inside of a collision, or an explosion in this case. Also, just to be technical, I use capital P's here for momentum because it's a system momentum. Okay, whereas I use lowercase p's up here for an individual object. That's a pretty technical thing. If you don't follow that, it's okay, all right? But it's kind of hard to see in my PowerPoint, but these are actually capital P's because this is a system of two carts before the explosion. This is a system of two carts after the explosion. Okay? Well, I want to know, how do those compare? Okay? Well, first off, what was the momentum of the two-cart system before the explosion? Yeah, it's 0, right? Because before the explosion, neither cart is moving. Right? No movement, no velocity, no momentums. After the explosion, the momentum of the two carts is the vector sum of the momenta. Right? So this is the momentum of the left cart plus the momentum of the right cart. And I'm using the F here again for final, right? Meaning after the explosion. But we just found out that what's true about the momenta of the two carts, of the two gliders after the explosion. We found out that those momenta are equal in size, but opposite in direction. Well, when you sum up two things that are equal in size but opposite in direction, what do you get? You get 0. So it appears that the momentum of the system before the explosion was 0, and the momentum of the system after the explosion was 0, which means the explosion didn't change the momentum of the system. That's really interesting. Right? So the momentum of the system before the explosion, which in this case was 0, happened to be the same as the momentum of the system after the explosion, right? Which was also 0. I wonder if that's true in more complex collisions, not just explosions where the two carts start at rest, right, and then explode, but like more normal collisions where maybe they're both moving and they run into one another. I wonder if that depends on what kind of collision we have. You know, if we use a collision where they bounce off one another nice, or a collision where they stick together maybe afterwards, does that make a difference? Sounds like a nice lab, doesn't it? And it will be, in fact, the lab that we're going to do after we finish this up and practice it a little bit with explosions. Right, so our goal in the next lab is going to be to see whether this is true. Right? Is this always true? Right? Or does it depend kind of on various things, like what's going on in the collision? Now, we get to do a cool thing here that we've only done, a few times before, and that is that we can, of course, do a proof of this as well. Right? So I want to prove to you that what we found in the lab, that the momenta of the gliders are equal in size but opposite in direction. So I'm going to start out by looking at what's going on during the collision. Right? We already know from what we talked about at the beginning of the unit, oh, here's our proof, sorry, that how much force does the left cart put on the right cart compared to how much force the right cart puts on the left cart. Get my notation there? This is the force the left puts on the right. This is the force the right puts on the left. Well, how big are those forces? Well, yeah, right? They are always, always, always equal in size and opposite in direction. And we call that Newton's third law. Right? Newton's third law of motion says that in any interaction, right, between two objects, the forces of interaction are always equal in size and opposite in direction. Okay, so we know this is true. We've even done, a lab on that to see things collide and all that kind of stuff, to see that the forces are always equal in size and opposite in direction. What about the time that they're interacting with one another? How much time does the left cart interact with the right cart compared to the time the right cart interacts with the left cart? Well, of course, they only interact with one another for the same amount of time, right? Hope you're okay with that. Which means we can then say, if we multiply here, that and since these are equal, I'm going to drop the subscripts, all right, because they're just the same size, right? Same amount of time. So this is the force the left cart puts on the right cart times the change in time, the amount of time its force is applied. And this is the force the right cart puts on the left cart times the amount of time it's applied. Well, since the times are the same and the forces are equal and opposite, then force times time must be equal and opposite. And isn't this impulse? So we've just proven that in the explosion, the impulse given to the side would be the right cart, right? Because it's the force on the right cart for the amount of time. This impulse on the right cart is equal and opposite to the impulse on the left cart. But didn't we find at the beginning of this unit that the impulse acting on an object is equal to its change in momentum? Right? And this is, again, the change in momentum of the right cart, because this is the force on the right cart, right, which would change the momentum of the right cart. This is the force on the left glider, which would change the momentum of the glider. And so that means these need to be equal and opposite to one another. With me? So the forces exerted between the two gliders are equal and opposite from Newton's third law. They interact for the same amount of time, so that means the impulses have to be equal in size and opposite in direction, which means the change in momenta have to be equal in size and opposite in direction. This, of course, is what we called the impulse change in momentum theorem, right? That the impulses were equal to the change in momentums. Well, in each case, right, a change in is a final minus an initial. So this is the final momentum of the right cart minus the initial momentum of the right cart equals, and don't forget the little negative here that we have to put in, right? This is the opposite of the quantity final momentum of the left cart minus the final initial momentum of the left cart. But in these explosions that we just did in lab, what's true about the momenta of the carts initially, before the explosion? Yeah, neither were moving, So those are both 0. And look what we have. So the physics that we knew before we even did this lab tells us that we should get a result in the lab that the momentum of one glider is just equal and opposite to the momentum of the other glider in an explosion where they both start at rest. And sure enough, that is exactly what we found. Again, this is doing some physics here. This is doing science. We get an experimental result, and we can theoretically understand why that result happens, right? And do a little proof or a derivation, if you will, right? And get that same result. Experiment and theory coming together to provide us a greater understanding of something that happens in nature.